Or in the more general mathematic case, area of extremal surfaces, space-like surfaces.
You ready to go, Tom?
I am, yes.
All right, good morning, everybody. Let's get started for the first morning session. Tom is going to graduate to QI in infinity dimensions.
Infinity dimensions. Okay, I'm glad we finally got there. Okay, so I'm going to talk about quantum information in infinite dimensions. So the first thing to acknowledge is that we're always going to be working with some Hilbert space. I'm going to assume it's a separable Hilbert space. Okay, that's not very controversial, meaning it has a countably infinite basis. But because now we're in infinite dimensions, we'll have the usual things. This is a vector space. It has an inner product, but it also has to be complete with respect to some topology, which is defined by the metric, which is defined using the Hilbert space norm. Okay, so meaning that if I have sequences of vectors in the Hilbert space, it will converge to some other vector if and only if this difference goes to 0. Okay, so now because we have this sort of notion of topology, we have to be careful with all of the things that we're doing. So for example, one thing that we talked about last time a lot were these subspaces and a relation between projections and subspaces. Okay, so if I have a projection operator, so projection operator on H, that's just some positive operator that squares to itself. Then this corresponds to some subspace of H that's closed. So this is a closed subspace, meaning that if I take the closure in this thing, I get back, using this metric, I get back myself. Good. And in particular, the relation between this projection and HS is that it's just an orthogonal projection. All right, so this is just 0 for any vectors in that subspace. Okay. Good. All right, so now we have the other thing that we have to acknowledge is the observables. What are the possible observables or algebra of observables on this Hilbert space? And because we're in infinite dimensions, now we have to think about bounded operators on the Hilbert space. So these are bounded operators. With respect to, so we have some operator on H, and we can define a norm of the operator as just the supremum over all vectors in the Hilbert space, a psi divided by the norm of psi. So this is how you define the sort of maximum eigenvalue in infinite dimensions. So that's a norm on these operators, and B of H is just the operators where this is finite, right? So B of H is just the set of A such that A is finite. Okay, and so this is a convenient set of operators to think about. It's not the only possible operators you can think about, and we'll come back to other kinds of operators in a little bit, but these are the ones that will define nice algebras that we'll work with. Okay, so B of H is an algebra already, which you can easily see. And what we're going to be interested in this lecture, so now, is subalgebras. So subalgebras of B of H, right? So we just denote that as A is some subset of B of H, but it's an algebra, so you can take products and linear sums. One thing that we'll always assume is that we're working with what's called star subalgebras, which just means that this is closed under the dagger operation. So if I just take the Hermitian conjugate, which is defined on these operators, I get back myself. Okay, so closed under dagger. Okay, so that's one class of algebras we'll think about. The other thing we'll think about that we introduced already is just the commutant. All right, so the commutant in this context is just the set of operators B in B of H such that B commutes with all of A, which I'll just write like this, okay, schematically. Okay, so now when we talk about such an algebra, we have to also say, because we're in infinite dimensions, we also have to say whether it's closed under some sort of topology, right? And so for that, we're going to have to introduce topologies on the set of operators. Okay, so A should be, doesn't have to be, but we'll take it to be, closed under some topology. And there's a few options that we have here. And the easiest thing to define for now is just A closure under the topology induced by the norm on operators, right? So the operator norm. So this thing is the closure, that's what I mean by this overbar here, of A. So it may be that A is closed, in which case I get back myself. I get back A, but if it's not closed, then I get something. And so this is the smallest closed subalgebra, star subalgebra that contains A. And it's closed in the sense that AN will converge to some operator generally in B of H. So if that's the case, if AN, some sequence converges to A in B of H, where convergence in this case just means AN minus A, operator norm goes to 0, then, so if that's the case, then A is in the closure. Okay, so we're just allowing for sequences to converge in this sense. Okay, good. Now, so if it happens to be the case that our algebra is closed under this operation, then A, so if, then A is called a C-star algebra. So usually, I should say for context, a C-star algebra is introduced not in the way that I've introduced it. It's introduced in a much more abstract way. So in particular, doesn't come with a Hilbert space. It's just some abstract set of operators with certain multiplication rules, a star operation or a dagger operation with certain conditions on it. And so that's usually how a C-star algebra is introduced. But you can always get a Hilbert space or a representation on which the C-star algebra acts on some Hilbert space. And there's this general construction called the GNS construction, which is being cut for time currently. Maybe I'll come back to it at some point. But yeah, so we can always find a Hilbert space on which this C-star algebra will act. All right. So that's one option. Another option is to use a different notion of convergence to define a closure. So the other thing we'll think about is the closure under the weak operator topology. So this is the definition, closure under weak operator topology. So this is a much weaker notion. So in particular, we say that a sequence of AN converges to A in the weak operator topology. So there's always some reference to that when you talk about limits in this sense. If matrix elements converge for fixed psi-phi on the Hilbert space, and it's for all fixed psi-phi. So you take matrix elements and you take limits, okay?
You probably don't want the n on the right-hand side.
Oh, yeah, thank you. I do not. Yeah, right, so this is another notion. In finite dimensions, the distinction between this kind of convergence and norm convergence is immaterial, it's the same thing. In infinite dimensions, it's not the same thing. So you can have sequences of operators that converge in this sense, but do not converge in this sense. Okay, so that's sort of why, well, it's a weaker notion because it's a weaker set of conditions that you have to set to satisfy, which means that you'll get more things that are converging. Okay. All right. So this is sort of the first important thing. So we have different kinds of notions of convergence in the space of operators. Yes.
So in the finite dimensional case, we need a sense of closure.
Yeah.
Was it implicit somehow, or?
I think it's just sort of implied by finite dimensions. Yeah. Yeah. The question is, in finite dimensions, is this notion of closure sort of implicit? And I don't think you even have to worry about it in finite dimensions. So I think it's just true. You can just check it. It will be true, generally.
Because we had a question up yesterday about infinite sequence of operators in finite.
Yeah.
Finite dimensions, one can consider infinite sequence of operators, and they need not.
Well, that question was my understanding of. So there's a question yesterday about taking infinite products of operators, and that I guess you can do, but it's not part of what you define as an algebra. So whether that is a thing or not, yeah, I mean it's some other structure. Yeah. All right. Yeah.
Did you say that this is like it's a strictly weaker notion of norm? Like all C-star algebras will be algebras with this norm also? Like all
Other way around. This will be a von Neumann algebra, and von Neumann algebras, all von Neumann algebras are C-star algebras. Yeah. Yeah. So we'll come back to that. I'll come to that. Other questions? Yeah. Yeah. I mean, why would you? I think the question is, why would you consider such a thing? And yeah, I think that's a reasonable question. Like, why? Yeah. So everything is finite in finite dimensions. Good. All right. So now, okay, there's one conceit here that I will have to sort of somewhat skip. I'll say a little bit. So this is a notion of convergence of sequences, and it's well defined, but it actually doesn't define the closure. So to define the closure, because this weak operator topology is kind of a different beast than this kind of topology. This topology is based on some norm, which is some metric. So you can define closed sets sorry, I should have said ages ago when I'm talking about topology, it's the standard notion of topology. You have open and closed sets and so forth. When you have a metric space, there's a natural set of open and closed sets. But when you have this kind of convergence, it's based on not a metric space. It's based on what's called a convex semi-norm. And given these sort of convex semi-norms, you can define a topology. And it's sort of much more involved. But because it's not based on a metric, we can't actually use sequences to define what we mean by convergence. Instead, we can use something that looks like a sequence. We can use nets, which are generalized sequences. Where AI converges to A if and only if A is in the weak closure, and this is weak convergence. And okay, so a sequence is usually a map from the natural numbers to the algebra. So this is like a map from N to operators in A. A net is just a map from a more general set than N, which has certain properties that means that it's nice for defining convergence. So technically it's a directed set, which is something with a partial order defined on it. Okay, so it's not super important actually. I have never used it in my research, so I find it not that important, but you know, when defining things, we'll need to use it. Okay, so I'll just write that. Net is a map from a directed set I in A, and it has a natural notion of convergence. Okay. It's actually independent of that notion. This is just what I mean by the topology. In that case, I can talk about nets even in this context where I have a metric space. So that comes in when I talk about this convergence. Where do I get a Hilbert space from the algebra? Yeah, the GNS construction. I didn't really talk about that, so I might come back later and talk about that. For the second option, okay, so let me get there. I'll just say it. So if in this case we have closure under the weak operator topology and I get back myself, then A is called, wait for it, a von Neumann algebra. Okay, and a von Neumann algebra is often like it's a different beast to a C-star algebra. Often when we talk about von Neumann algebras, we mean a subset of operators on a Hilbert space. So it always comes with a representation, if you like. Von Neumann algebras typically always come with a representation. Okay, C-star algebras, that's not the case. Yeah. This sentence? Natural notion of convergence. This line, net map is a map is a map from the directed set I to A. Thanks for my editing. Good. Yeah, it's a partially ordered set, which so if I have two elements in it, ij is in I, then there's always a greater element that's greater than both of them. Then there exists k in I, k is bigger than I. Right, so it's partially ordered, so you can't always compare things. Right. Nothing here, because I just use sequences. But here is the correct definition of closure. Yeah. The correct technical definition using nets. We should use nets, and I'll let you read about them more yourself. Okay, good. Yes.
You mentioned that like for one algebra, usually comes with like a representation.
Yeah.
Does that mean like you have a Hilbert space you act on, or
Yeah.
what does that mean?
Yeah, that's what I mean. There's a Hilbert space. Okay. Now, all right. So there are other topologies that are sometimes useful to know. I'll just mention one other. There's many actually. And that is the strong operator topology. And this is the statement that SO, a sequence. Yeah, so this is sometimes the notation SO limit limits to some operator if and only if AN minus A psi converges to 0 for all psi in the Hilbert space, for all fixed psi in the Hilbert space. So yeah, basically, instead of taking matrix elements, you just take the product on a fixed state and take its norm in the Hilbert space. Right, so that's just some other notion of convergence. It's not the same sort of matrix element convergence. It's slightly different. Okay, so there's sort of an order on the weakness of these topologies. So we have the weak operator topology is less than the strong operator topology is less than the norm topology, which is just based on the norm, the operator norm. And this is really easy to see. It's just based on some inequalities that you can easily sort of prove. AN minus A phi is less than, so let me do it this way, psi, norm of psi times AN minus A phi, which is less than just the operator norm times the norm of the two vectors. Okay. Okay, so sorry, that's hard to read probably. So yeah, so just based on these inequalities, you can show this kind of thing. But basically, another way to think about this sort of inequality, set of inequalities, is that more things converge here, more things converge, meaning that if you take closures, you get bigger things, okay, and less things converge here. And if you think about what that implies for the algebras, that implies that a von Neumann algebra, the set of von Neumann algebras, as I've defined it, is a subset of C-star algebras. So von Neumann algebra is always a C-star algebra, but it has more structure. Yes?
So the C-star algebra goes with the weak operator?
No, C-star algebra is with a norm topology. It's this guy. Yeah. Another thing to say about this is these kinds of notions of convergence. This is kind of like a pointwise convergence. I just make it converge on, in certain matrix elements, and the C-star algebra is a uniform convergence. This is sort of a uniform thing. Okay. Good.
Tom, since you introduced the strong, are you going to mention what happens when you do that on a star algebra?
Yes, I will in 2 seconds. Yes. Yeah. Yeah. C-star algebras are less convergent than the normal. Did it? Yes. Yeah.
So shouldn't the subset be the other way around?
No. So less things converge means that the closures are always smaller. So that means that yeah. This is definitely a subset.
I meant this less than.
Yeah, so this is a notion that I haven't defined, but there is a notion on topologies, and there's an inequality, and this is the correct way. And this is the right thing to say. Now, why it means that, yes, it should be clear, but basically, yeah, I mean, if you check convergence, if you use a closure here, more things have converged, then it will also be closed under the norm topology, right? Just because it's, it gives you it always gives you a smaller set, right? So yeah, I mean, can I say this in a better way? Yeah. Yeah, that's true. Yeah. I should say that. Yeah, you're not actually using the von Neumann algebra closure as. So you're taking the closure and then checking if it's a C-star algebra. I think that's the way to say it. And then if you do that, you'll use this inequality to show that one is zero. Yeah. Good. Now, all right. So there's a better way to define these things. There's a really nice sort of algebraic way to define what a von Neumann algebra is, and that goes under the name the von Neumann's bicommutant theorem. Oh goodness, this thing. Okay, so the basic idea is the following. Von Neumann's bicommutant theorem. The basic idea is if I take some set of operators, it doesn't have to be an algebra, it doesn't have to be closed under products, but I do demand that it's closed under the dagger, so sometimes it's called a star set for that reason. Then, firstly, S prime is a von Neumann algebra. And why is this? Well, this you can just convince yourself. I'll go through some of the steps. So if A1 and A2, so firstly we have to check it's an algebra. So if they're both in the commutants, then the product is, just because of this relation. Okay, and I'll just use a bit of an abstract notation by putting the set here itself. Hopefully you know what I mean by that. All right, just using this usual relation on commutators. So if this vanishes and this vanishes, then that has to vanish. So indeed, it is an algebra. It's also, also linear combinations. It's clear that that's true. And then you just need to check the closure. So check closure. So if I have a sequence, or really what I need is a net of operators that converges to some operator in B of H, and these things are in S prime, then you can just, yeah, thank you. Yeah, that's right. Yeah, so if this net or sequence is in S prime and it converges to some operator in B of H, then you just check, all you have to show is A is also in S prime, and you can easily do that in matrix elements using the weak operator convergence. So let me just write the equation so you see it. What do I say? Yeah, so if I take the limit on I of matrix elements, right, then by the weak operator topology, this matrix element will converge, right? That's the definition. Of course, you have to act with operators here and here, but it's still the same thing. And so this just converges to phi AS psi. And this is 0 because each of these is 0. And so this has to be 0 for all phi psi. And so that actually means that has to be 0. So it's actually closed. So S prime weak operator closure is the same as S prime. So it's a von Neumann algebra. One thing to note is that this means that von Neumann algebras always have a unit operator, right? Because that always commutes with everything. Yes?
What if S is not a star set?
Then you may not get a von Neumann algebra. If it's not a star set, then you won't get something that's closed under the dagger operation.
But I still get the algebra.
Yeah, you get an algebra. Yeah, it won't be very good for quantum mechanics, I guess, because there's no dagger. Yeah, yeah.
Sorry, are you assuming that there's already that the AI are already converging to A?
Yes. Yeah. That's what I mean by closure, right? So that has to be converged. I mean, I could have some random set of operators that don't converge, but that doesn't tell me anything. But suppose it does converge, it will converge to an operator in B of H. I just have to make sure that it's in the subset, which is S prime, and that's what I'm doing. In the weak operator topology.
Or I guess the assumption here is for AI.
Yeah, I should have said. Sorry. Yeah.
By the way, do I always get a star set by taking the union of S and S dagger?
Yes. Good. Okay. So that's part of the bicommutant theorem. The actual thing is if I take 2 primes, right? I can do it again. I take S prime, do it again. Now this is the von Neumann algebra generated by S, right? So you can easily see that S has to be an S double prime. S need not be an S prime, but S has to be an S double prime. And another way of saying it is it's the smallest von Neumann algebra that contains S. Okay, one warning is that the weak closure of this is not equal to S double prime. It's something else. That's just some closure of a set. However, I lost my spot. Really did. Sorry. However, wow. If A is itself a star algebra, need not be closed under anything, then it is true that A double prime is the same as the weak closure. And in fact, it's the same as the strong operator closure. Often, we could have used the strong operator closure in this discussion. You get the same results, basically. So if you close things under the strong and the weak operator topologies, they're different topologies, but if they're acting on if you do a closure on some algebra itself, an algebra is a convex set, and the topologies agree on convex sets. So you always get the same thing. All right. All right. So this is a beautiful characterization of what a von Neumann algebra is. we just need to take, well, we could start with an algebra. And so, yeah, so let me just say it that way. So von Neumann algebra is one that is equal to its double commutant. Von Neumann algebra is a star algebra A such that A double prime is A. Okay. Okay, so good. So there's a few extras that I have to mention now that we've done this. Some extra results that are sort of trivial from this. The first one is that if I have two von Neumann algebras on the same Hilbert space, then the intersection of the two, the set intersection, is also a von Neumann algebra. It's often denoted with this wedge, even though it's the same as the intersection. So that's one. The union is not a von Neumann algebra because it's just a union. It doesn't have to have products and so forth. But you can define a notion of the algebra generated by two algebras just by taking the closure of the union, taking the double commutant. So good. And so then you have some results about that. This thing? Yes, yes. Right, so basically once I have three primes, I can just cancel two of them. So that's one thing that you can always do. And okay, so then there's other things. So for example, this implies that if I take, so now if I do take the commutant of this guy, for example, then there's three commutants here, but that's the same as I said as one commutant. So that's just by definition, this thing. And it's not actually hard to check using the rules of the commutant that this is the same as A1 prime intersect A2 prime. Right, so this is that intersection. Another thing that's also not very hard to check is if I have a subalgebra, they're both von Neumann algebras, then B prime, if I take the commutants, the inclusion goes the other way. So the subalgebraness goes the other way. Good. Okay. Now, there's a notion of a center. Z of A is just given by the intersection of A with its commutant. So it's a set of operators that are, so it's an algebra itself, but they're common to A and A prime. It's a commutative algebra because of how it's defined. So that means that all operators commute with themselves. And for the most part in these lectures, we're going to focus on factors. A factor is a von Neumann algebra with trivial center. So often written Z of A is just complex numbers times the unit. Right? So that's what we mean by the trivial algebra. It's just the identity. Okay, and the reason for this is basically that, from a math point of view, the reason to focus on factors is you can always decompose an algebra into a direct sum of factors. So you just need to think about the factors, and then, so if you can classify them, for example, then you're done. So let me say a little bit how this works. Let me give you an example of this, and then, Yeah, no, that's fine. No, it's the next thing that, yeah.
Well, I just had a general question. If you had an algebra of operators and you wanted to work with a closure that under one of the topologies, what is the approach for doing that? Because I can imagine you could have like an algebra that where like sequences of operators in that algebra don't have like none of them have any limits. Anyways, under any of the topologies. Like I guess my question is like, how do you recommend taking the closure of an arbitrary?
It sort of depends on the context, but yeah, sometimes this double commutant is easy to work with, sometimes it's not. So yeah, in that case, you need to think about these nets and generalized sequences and whether they converge, okay? And yeah, you'll always find some things that converge. For example, if you just take a sequence of the same operator, it obviously converges to that. So there's some things that converge at least. That is one context where you do need to talk about directed sets. So actually, I guess that doesn't come up very often. For me, at least, it hasn't come up very often. Okay, so let me give you an example of how this works. This is not the most general discussion of centers, but it's useful to know. So if we go back now to finite dimensions and we ask, well, what are all the possible von Neumann algebras in finite dimensions? And you can actually classify them. And they have centers, but they always look as follows. So finite dimensions. In finite dimensions, the general von Neumann algebra just looks like so it acts on some direct sum of Hilbert spaces where we have a sum over, let's say, n. We have some Hilbert space for which the algebra will act on, and then we have the environment for that algebra that I'll call En. Okay? And then the algebra itself is just a direct sum over B of HAI, AN, tensor the identity on the environment. And then the commutant is not hard to work out. It's just a direct sum of the identity on AN times B of HEN, like that. And the center itself, Z, is just the intersection of these two things, is just the direct sum of complex numbers, Zn, where Zn lives in C. And how you should think of this, and really this whole decomposition, is that on this kind of direct sum Hilbert space, you have these blocks, okay? So you have blocks, operators look like blocks. And the center itself would be, this would be some matrix that has Z1 here, the identity A1, E1, tensor E1, and then Z2, identity A2, E2, and so forth. Okay, so down the diagonal you have these blocks. Okay, so that's the general structure of a finite dimensional von Neumann algebra. And one thing to acknowledge here is that Z, if I just, Z prime is Z, it's equal to itself. So that means I can present this in another way. This is just equal to A union, sorry, what am I saying here? Z prime is not equal to itself. Let me just, what was I going to say here? Z prime is A union A prime. And that's just the direct sum of all operators on H1, Hn, En But this is not all operators in the Hilbert space. There are more general operators. They're just all operators that live on the blocks. You can have transition elements, and they're just not described by this von Neumann algebra. Okay. Now, another thing to say is that the center is a commutative von Neumann algebra. So all operators commute with themselves. And a commutative, what is a commutative von Neumann algebra? You should think of physically as just a theory of classical probability. So a general thing would be some functions on some measure space. When that would define a von Neumann algebra. So for example, functions on R equipped with a norm, which is like the operator norm. The norm of f is just the supremum over all x, f of x. And this space is sometimes called L infinity of R. So these are the measurable functions with finite norm. And this is an example of a von Neumann algebra. And it's clear this is some notion of classical probability. So the thing about this kind of space where we have both commutative and non-commutative things is physically would be a setting where you have classical and quantum things happening at the same time. So it's a setting where you have sort of mixed classical quantum states and things like that. Good. Yeah, multiplication is just the product of two functions. Yeah. So f times g is in L infinity of R. Okay. Okay, good. Now, all right, so now let's move on. So now that we have von Neumann algebras, we're going to focus on von Neumann algebras from now on. Let me just say that. Now let's think about states on von Neumann algebras. So states on von Neumann algebras. Well, a state, again, is a linear functional, which is just a map from the operators to the complex numbers. It's equipped with a natural norm, which is just acknowledging that this is some kind of dual space. So you just take all operators and feed them into rho, and then divide by their norm. So that's the norm on these linear functionals. Once we have a linear functional, we have various qualifiers that come along with it. So when you read about these things, you'll see this list of qualifiers that appears in front of a state. And so let me say what they are. So positive. In general, this could just be a linear functional. It need not be positive, and you can still define the norm and so forth. So rho. But if it's positive, if I feed in positive operators, then I should get something that's positive or equal to 0 plus. It is useful to think of it as being, it's often useful to take it to be faithful. So faithful means if I feed in any positive operator and it gives me 0, that operator had to be 0. Okay. This is a notion that I'll come back to quite a lot, but you should think of this as the equivalent of fully entangled in the finite dimensional case. So it would require a density matrix that is full rank, for example. Yes? Sorry, yeah. I don't know. I changed my notation, I think. Thank you. Yep. Okay, good. So we have faithful, positive. Another qualifier. That we get. Is some notion of continuity. Okay, we're in infinite dimensions, so we always have to say something about things being continuous or how they're continuous. So we have to have, some notion of continuity. Okay, and so there's various notions that you can think about. So one is if you just take rho to have bounded norm, then this is usually what we mean by a linear functional in the topological sense. But this is not natural for von Neumann algebras. It is natural for C-star algebras. So when you read about states on C-star algebras, they'll be continuous in this sense. For a von Neumann algebra, we're more interested in states that are called rho is normal. So that's the qualifier, and it just means that it's continuous. It's continuous as a map from A to the complex numbers, where we equip this with a weak topology. Weak topology. And there's a subtlety here I have to include on bounded sets. But basically, it means that if I have sequences of operators that converge in the weak topology, then the matrix elements should also converge, right? So if AN a weak operator. Okay, and so that's very important. The states that we're picking will be these normal states. Yes. Yes, it's a stronger requirement. Yes. So these normal states have a name. They're given a symbol, which is A lower star, and that's a subset of linear functionals, which is just A upper star. So these are the normal ones. They also need not be positive, but yeah. Oh, that's the same thing. It's a plus. That's okay. I should really fix that. Yeah. Okay, good.
So when you say qualifiers, do you mean like these are properties that we want of our state, or these are properties our state could have?
Yes, exactly. They're things that we could have. So you'll see, consider a positive, faithful, normal, blah, blah, blah state. And that's what I mean by qualifier. Right. So sometimes people will ignore that, but you probably should say that. Yeah, so this is the notation that we use for the states. So it's a slightly different, it's a funny thing that this is a common notation for linear functionals, right? And then this is this special set of linear functionals. It's sometimes called the predual. Okay, there's a whole lot of things to say about that, but I won't say much about it. Another qualifier that I'll come back to, let me just say it real quick, is your state could be tracial, which means, so we usually gets a different name, tau instead of rho. It just means that if I put in two elements, then I can switch their order, just like cyclicity of the trace. Right? So this will be important later. Okay, so one thing I was going to say now, but I'll drop it. I'll just mention it, is that you can also talk about quantum channels on von Neumann algebras. All the same kind of things arise. So you have to also include qualifiers. Completely positive is a standard thing. Normal just means it's appropriately continuous. So it's a map between von Neumann algebras preserving the natural notion of topology, and so forth. OK, so now let's at least start talking about modular theory. OK. So modular theory, you should think of as a way to introduce quantities that are sort of the things that you would like when talking about quantum information. So quantum information, we want to have sort of quantities that tell us about the informational content of the theory. And so for that, usually we'd use a density matrix. We would compute entropies with the density matrix. Density matrix is not something that's well defined on a von Neumann algebra, so we have to replace it with something else. What is that something else? It's modular theory. OK, and so let's get into it. So we're thinking about some normal state. So normal state rho. Yes. It's an example of a state, right, which satisfies an extra property, right? So it's another qualifier. Again, this is a qualifier. Sorry, this is the this is the qualifier. Yeah. OK, so we take a normal state on rho, so on A, rho on A, and we seek a purification. OK, so this may not always exist because I'm working on a fixed Hilbert space, right? So I'm not doing this thing where I'm allowing different representations. I could, of course, but we'll come back to this. We don't really need to do this. So I'm going to seek a purification in the Hilbert space. And that would mean that rho can be represented as just matrix elements of psi restricted to the algebra in question. Okay? Matrix elements of psi, I could put any operator here. But let me just restrict to A, which is some subset of all the operators. And so this is also sometimes denoted omega psi. Right, so omega means just this expectation. OK, so I'm going to assume that this exists for now, and we're going to develop modular theory for this wave function. OK? And we'll come back to how it depends on rho and so forth. So we need some properties of psi to develop modular theory. We need psi to be cyclic and separating. What does that mean? So cyclic and separating so psi to be cyclic and separating for A. So it depends on A. And it's a property of the purification. So cyclic just means that if I act with all operators on psi, that's some set of states in the Hilbert space, and I take the Hilbert space closure, then I get all of H. Right? So I can get any state in the Hilbert space just by acting on psi with an operator in the algebra A. So this is not always true, but when it's true, it's going to be nice. And separating. Separating is just the statement that if A psi is 0, then A is 0 for all A. So one thing to say is that the separating condition is intrinsic to the state. And it's not hard to see that it's equivalent to this faithful condition, rho. So we'll add that as a qualifier to our state. The cyclic condition, however, depends on the purification, right? So it depends on the environment. So yeah, depends on environment. Okay. The other thing to say is that these two qualifiers for the state psi switch under commutant. So this is an easy exercise. I'll leave it as an exercise to prove this. But you can show that if exercise is that if psi cyclic for A, so here are two things, separating for A, then they switch psi cyclic for A prime, psi separating for A. And this is another way to see that the cyclic condition depends on the purification, which is the commutant, right, in this language. Okay. Good.
Could you repeat what the subscript A means in the definition?
Subscript A. This thing, that means restriction. It means it's kind of a formal thing. You don't really need to talk about it. This state is only defined on A's, on operators in A, but not all B of H. However, matrix elements are defined in all B of H. So let me just restrict them to A. So I'm just telling you that I can only put in A, right? Yeah. This thing is what you would call a partial trace usually, partial trace over the commutant. That doesn't always exist, but this restriction always exists. So it's a well-defined notion, always.
Think about the fact that there are other purifications that's we're only considering like an algebra A, which is a subset of all bounded operators.
Yeah.
At least in the finite case, then if it was all the bounded operators, the purification would be unique, right? When it comes to phases and things.
Well, it depends, yeah. So in the finite case, I talked about different purifications, which lived on different Hilbert spaces. Yeah.
I understand, but if you were to purify in the same space and the algebra was a whole set of operators, then the purification would be unique, right?
Well, it's not unique, no. I didn't say this, but if I take a unitary operator on the commutant, this is another purification. Basically because it commutes with all operators here, and you can kill it.
That doesn't trivialize if the commutant is only the identity.
Yeah, but the commutant is often never the identity.
Yeah. But what I'm trying to understand is that the fact that it becomes non-unique is because we consider it like a subset of all operators.
Yeah.
Thanks.
That's right. That's correct. Okay. Yes.
I was just wondering why for some purifications, like is the context here that we have some like set of operators which form an algebra and we know like the implementation values of some state, like some unknown state rho for these operators, and we're trying to figure out what the total state might be, like the inner state?
Yeah. So what? Yeah. So I guess the question is, yeah, why are we seeking a purification? Is that one way to summarize it? I claim that to develop modular theory, we need that purification. Okay. And we'll come back to the question of whether it exists. Okay. Good. So now with this cyclic and separating vector psi, I can develop modular theory. And the idea is to define some operators that turn out to be sort of proxies, in some sense proxies for the density matrix. So I'll give you some definitions, and then we'll see how to think about it by just sort of relating it to what happens in finite dimensions. So what we're going to do is that we're going to define some operators. Define operators S and F via these equations. S A psi is equal to A dagger psi. F A prime psi is A prime dagger psi, where this is for all A, and this is for all A prime in the commutant. Okay, so we're defining the operator by how it acts on certain states. Okay, that's just how we define it. This is a consistent definition of an operator if you realize that S and F are antilinear. Right, and they're antilinear just because of this dagger over here. So that means that if I act on linear combinations, I have to complex conjugate the coefficients, right? The usual definition. Yes. Yeah. So good. Yeah. So I should write that. Assume psi cyclic and separating. Okay, so what does that give us, the fact that it's cyclic and separating? Well, it gives us the fact that these operators are what are called, so these operators, as we'll see, are unbounded operators. Unbounded operators. Unbounded operators can never be defined on all states in the Hilbert space. If they're defined on all vectors in the Hilbert space, then they're bounded. You can show that. So they can't be defined on everything. And we haven't defined them on everything. We've defined them on this sort of set of states. But because of the cyclic condition and separating for A prime, they're densely defined, meaning they are defined on enough states in the Hilbert space. Right, so they're defined on a set of states in the Hilbert space that is dense, but it's not everything. So it means I can close it and get everything. But that doesn't mean that I can use the closure to define this operator. Okay, for unbounded operators, because they're unbounded operators, they're a little bit difficult to work with. And so probably you might have skipped this section of quantum mechanics, maybe you didn't, and then you're fine. But yeah, let me say a few things. Because of time, I'm going to have to be limited. So whenever we have these unbounded operators, we have to define the domain that they're defined on. So we call that D of S. D of S is the domain of S. And it's here. It's clear that the domain is just this without the closure. And D of S is just A prime psi. So given a densely defined operator like this, you can always define its adjoint. So we can always define the adjoint of S and F. And there's two things about this adjoint. I claim, and this is going to have to stay as an exercise, that F is S dagger on whenever F is defined. So on A prime psi. Okay? So when acting on these kinds of vectors, this equation is true. But S dagger has some independent definition, which actually means it's defined on a bigger set. It's not defined on everything, but it's defined on a bigger set. So the actual thing we should say is that by definition, we say that S dagger is an extension of F. That's the notation, which just means that the set on which f is defined is a subset of this, and they're equal on that subset. Right, so that's what we use. And you can also show S is contained in F dagger. Okay, and so why is this useful? Well, this is useful because it proves that the adjoint of the operator S dagger, because F is densely defined, that necessarily implies that S dagger is densely defined, and that means that S dagger is a good operator. A good unbounded operator. So okay, I'm just not going to have time. What should I say? It doesn't. Yeah, so basically F is defined on some set of states. Okay, I've just given you the definition. S dagger has an independent definition, and that's what I mean by exercise here. You have to go back and remind yourself what that is, and it turns out to be a larger set. Yeah, so it includes more things than the definitional set. Right, and so this means that. Okay, let me just sort of write the thing. F dagger densely defined. And that means that S and F are what's called closable operators, which means I can extend them to a larger set where they're much better behaved. And extend them. Their extension is called S bar. One way to define the extension is just to take the dagger twice. It's very similar to taking a double commutant. And the same for F. Basically, closable operators are the nice operators that have similar properties to bounded operators. So we can do things with them that we would like to do with just general operators. There's something called the polar decomposition, which we're going to use. We can take functions of them, and so forth. If we didn't have that, we couldn't do all these things. Okay, so this is necessary, and this is sort of part of the structure. Okay, so I have to I was going to define this a bit more carefully, but I'll have to skip that. You can remind yourself. So closed operators. So closable operators are ones that have a good closure, and now we'll work with the closure S bar and F bar, and the closure is still not defined on all states in the Hilbert space, otherwise it would be a bounded operator, but they have some nice properties. So consequences for S bar has a polar decomposition. Which for a linear operator means you can write it as a unitary times a positive operator. For an anti-linear operator, means I can write it as an anti-unitary operator times a positive operator that I'll denote as delta to the power of a half. Delta is independently defined as just S dagger S, like this. So that's the polar decomposition. So we get these two operators, J and delta, that will be important in modular theory. Okay, good. So let me say a few trivial consequences. So firstly, by the definition, you can see that S squared has to square to 1. And this implies that J squared squares to 1. And it also implies something about the commutation relations between J and delta that I don't have time to explain. But these two follow from this condition. And we will use these. So those are some simple consequences. These operators annihilate the state in question. So psi, that's not so hard to see just because S annihilates the state. So it doesn't annihilate, it holds fixed the state. So does these operators. So S bar psi is psi, and J psi is psi, delta psi is psi. Okay, there are some trickier consequences that I'll write, and then I'll have to end. The first one is that I can define what's called an isomorphism on the algebra, which is an example of a quantum channel, by the way, by just conjugating by this delta. And this thing is in the algebra A, and so that's non-trivial, it turns out. And I can also define a little j as conjugating by big J, and that thing is in the commutant. Okay, so J switches between A and A prime. And okay, let's say one more thing. The other important consequence of this is something called the KMS condition. And in fact, the KMS condition characterizes this alpha S. So I'll finish there. Just write that out. So KMS condition. So there exists an isomorphism between A and A. That's sort of a representation of the group R, because this is additive, so alpha S composed S plus T, such that, and we can actually state this just in terms of intrinsic to the state itself. So such that it holds fixed the state and satisfies this KMS condition. This thing has an analytic continuation to the strip, to the complex strip. So let me draw that here. So the original function is here along the real axis. So this is imaginary S. This is real S. The function lives there. You can analytically continue it to the strip between 0 and I. And when S is equal to I, this has, up here, this function becomes rho of B alpha SA. So A and B flip in this definition. So this is called the KMS condition. It is true for thermal states for thermal states, the thermal density matrix e to the minus beta h satisfies the KMS condition. For time evolution, where this is time evolution, and the strip has width beta, right? So the temperature is involved. Here, we have some generalized notion of this KMS condition that arises for any state. So it need not be an equilibrium state like the thermal state. It's for any state. Of course, it has some temperature, which is fixed to be 1 just by normalization. And so that's it. So modular theory has given us this sort of generalization of this KMS condition for non-equilibrium states. So that's where I'll end today. Yeah. Okay.